Okay, welcome everybody for the second talk of today. It's a pleasure to introduce Noam Berger from TUM to talk about stationary Hastings-Levitov. Thank you, Noam.
So, thank you very much for the invitation. I wish I could be physically in Israel, but at least I'm virtually in Israel. And I'm going to talk today about the stationary Hastings-Levitov, and this is based on joint works with Yaakov Kagan, Evyatar Procaccia, and Amanda Turner. So let me start with the background. I guess there will be a lot of background. So I'll start with explaining the diffusion limited aggregation, even though what I'm going to speak about is not exactly the diffusion limited aggregation. So it tries to model aggregation. So in many physical systems, what happens is that you have a collection of particles, an aggregate. So for example, the one at the top here. And then the way it grows is that some particles come from the outside and then join at a certain point the existing aggregate. And there could be many different rules as to how it happens. I'm going to speak about a few specific rules. And in this picture, which was presented to me by Evyatar, who's sitting here, it's a Petri dish with very small amount of nutrients, so not enough nutrients. So the bacteria start here on this line, and then it grows whenever bacteria here multiply, and the bacterium multiplies if it gets enough food. So the nutrients somehow diffuse, maybe in a Brownian fashion, or maybe in a different fashion, here in the Petri dish, and they land. Eventually, a nutrient lands on a bacterium, and the most naive model would be that a bacterium that received a piece of nutrition then multiplies. As far away as this is from reality, it turns out that if you actually look at the shape that this aggregate produces here, it does look as if that's what happens. So this is one physical model. There are many other possible physical models where particles are diffusing one way or another and then joining an existing aggregate. So the diffusion limited aggregation, the DLA, is a very simple model that try to capture this aggregation. Simple, but at the same time also extremely hard. So here I have explanation of what is random walk, but I think this I can skip here. And the diffusion limited aggregation, or DLA, in Z2 is the following model. So we start at time 0 with 1 point. Then for time 1, we take a point that produces a random walk from infinity until it attaches to the initial point, and then another point comes from infinity, does a random walk until it attaches to the existing aggregate, and so on. So this beautiful animation was produced by Evyatar. And then we wait. After a long time, this grows, and this is the famous DLA, the infamous DLA. And what does it mean? Okay, so I said that the particle comes from infinity or from very far away. What does it mean? So it means that the attachment point of the particle is sampled according to the harmonic measure. So what is the harmonic measure? So we work in 2 dimensions, so we know that the random walk is recurrent. There are also equivalent things in higher dimensions, so the recurrence is not that critical, but the harmonic is recurrent. So whichever point in which I'm going to start the random walk, eventually I'm going to hit the set A, where the set A stands for the current aggregate. And a not so difficult theorem says that for every finite set in Z2, if I look at the heating distribution starting from a far away point X, this limit exists as X, or absolute value of X, goes to infinity. And this limit is called the harmonic measure of A. So now we define the harmonic measure of A. And what we do every time is that we add a particle based on the harmonic measure. Okay, so what do we know about DLA? The answer is very little. So I can show you, I will soon show you a few simulations, but there's very little that's rigorously known. So in particular, there's no proof that the DLA does not converge to a ball, or that it doesn't just spread arms that grow. So maybe linearly is known that doesn't go linearly, but it doesn't spread long arms. So there's really no shape theorem. It doesn't go linearly. That was proven by Kesten, and that's, to the best of my knowledge, the only proven result. So at time t, the DLA is contained in a ball of radius t to the 2/3. So it doesn't go faster than t to the 2/3. But simulations show that it actually goes much more slowly than t to the 2/3. And this is not proven. Also not proven it goes faster than t to the 1/2, which would be the combinatoric lower bound. So there are many open problems. One of them is the growth rate. So upper bound t to the 2/3, but what is the growth rate of the DLA? What is the structure of the limiting set? Is there a way to make sense of a fractal dimension of this limiting set? And if there is, what is it? Then there's a question of number of arms that I don't want to get into, but if you look at pictures of the DLA, which I will show you soon, you see that it grows in certain arms, and then physicists have a somewhat baseless conjecture that there should be 5 arms. Okay, so these are some of the main problems regarding the DLA. And the same way that we define the DLA on the lattice, we can also define DLA off lattice. So we can define a continuous version of the DLA. So this is defined, instead of a particle moving on the lattice, we have in the continuum, we have a ball-shaped particle, or any other shape, which performs a Brownian motion, again starting from infinity in the sense that I explained, and it runs until each particle performs its Brownian motion until it attaches to the existing aggregate, and mathematically it's equally intractable. So still, essentially, whatever you ask, you don't know the answer. So here I have 2 homemade simulations of the off-lattice DLA. And here you see in this simulation, this is 120 particles, and this is 400 particles, but here some of the particles are outside of the frame. But here in the small simulation, I think you can see 4 arms, and in this one, I'm not sure how many arms you see, but there's a clear, so from looking at the picture in the simulation, there's a clear arm structure. It's not so clear how to mathematically define this, what an arm is. So that's a DLA, and then people were looking for simplified models of the DLA, and these models were first based well, most of those models are based on the following observation that connects harmonic measure with a simple observation, connects harmonic measure to conformal maps. So we know that the attachment point is sampled according to the harmonic measure. We also know that the harmonic measure is conformal invariant. So here's an algorithm. It's not a practical algorithm, but a thought algorithm for sampling a boundary point of the aggregate of any set A according to the harmonic measure. So let F from the complement of my set A to the complement of the unit disk be a conformal map, some conformal map. Then choose a point Y on the boundary uniformly. Why uniformly? Because for the disk D, the uniform measure is the harmonic measure. So choose a point uniformly on the boundary of the disk, and then take F inverse of this point Y, provided that this makes sense, right? The conformal map, you need a conformal map that somehow extends to the boundary. So this would be an algorithm for sampling a boundary point of a set A. So I can, so instead of running a Brownian motion the way I actually did in the simulation that you see here, I could find the conformal map that would send this aggregate to the unit disk, then sample a point on the unit disk and project it back. On the boundary of the unit disk and project it back. Okay, so there are at least 3 different approaches, and all from approximately the same time, that use this simple observation. So the most famous is Oded Schramm's SLE, which didn't try to do the DLA, but if you look, for example, at the loop erased random walk, then again, there's an issue of harmonic measure, but the harmonic measure is not all over the aggregate, but only at the tip. So Oded Schramm was using this observation and went into completely different directions with great success. Then another approach is that of Carlson and Makarov from 2001, where they define some sort of a deterministic DLA model. So the model that Carlson and Makarov introduced was, so we say that at the DLA, we randomly attach a point according to the harmonic measure. So if you believe that there's some law of large numbers, and in fact there isn't, but if you believe that there's some law of large numbers, then you can try to model it by a deterministic growth that says that the growth around at every point on the boundary would be proportional to the harmonic measure at that point. So if you start from a disk, it just goes like a disk. It just goes uniformly like a disk because it's deterministic. There's no. But if you start with some defect on the disk, then the defect is going to grow, and you're going to get very interesting and complicated shapes. So Carlson and Makarov defined this deterministic DLA model and studied it. And that's all I'm going to say about Schramm's work and about Carlson and Makarov. The third approach from 1998 is that of Hastings and Levitov, and that's the one that I'm going to speak about in this talk. So we focus on the Hastings-Levitov. So what is the Hastings-Levitov process? So Hastings-Levitov and Levitov proposed a family of processes, HL alpha, Hastings-Levitov alpha, and the simplest and easiest is alpha equals 0. And it defines as follows. So first of all, consider the conformal map phi delta. And what does phi delta do? Phi delta is a conformal map that, maybe I'll try to switch to my other board, so switch back and forth between the two boards. So let's see if I'm able to do this. So phi delta is the following conformal map. So I take the unit disk plus, maybe that's the wrong place. I take the unit disk plus a little interval. The interval is my particle of length delta. So phi delta is a conformal map, conformal from the complement of the unit disk to the complement of this picture, of D plus D union one plus delta. So the unit disk plus this, the whole thing. Complement, it's conformal, and it should send infinity to infinity. So there are a few degrees of freedom in choosing conformal map. So the infinity should go to infinity, and the derivative at infinity should be a positive real number. So with these two requirements, we're now setting exactly what a conformal map is. So it's a conformal. So it's a conformal map that just adds a little interval to the unit disk. So that's the, so it's phi delta. So that's phi delta. And then we take theta k to be IID uniform angles, so uniform points on the boundary. So the boundary of the disk. So these are points on the boundary of the disk that are chosen according to the harmonic measure, which is uniform on the disk. And then we take a sequence of length delta k, which we think of as all being the same for now. And we take phi k to be the conjugation of this phi delta with the length delta k with the rotation at angle theta k. So if phi delta takes exactly this interval, the phi delta k takes this interval because of the conjugation when the interval is put in a different point, in a random point. And then we define psi n to be the composition of all of these functions. And we focus mostly on the simplest case. So I will soon explain exactly what this does. We focus on the simplest case where all the delta k's are just equal, and this is HL0. Okay, so what is this conformal mapping that we?
Just 1 second. Where was the alpha never on this slide? The alpha never entered at all, right?
So on this slide, I explained the case of alpha equals 0. So that alpha equals 0 is the case where all the delta k's are equal, are all the same. For alpha greater than 0, the choice of the delta k is going to be more complicated, and I will explain it. I will explain it later, but I will not. It will not be very important for this talk. Okay, so here is what happens for other values of alpha. So for other values of alpha, we take delta n to be delta times something that depends on everything that happened until now, and the alpha is here in the power, and I will explain where exactly this comes from, but not now. Okay, so what is the what does this do? This the Hastings-Levitov. What does so essentially what happens here? So let me maybe I'll switch back to I switch to my other board, and then I'll go back to this beautiful picture. So we defined, my other board turned itself off. So so we had phi 1 composed on phi 2, and so on composed on phi n. So what is it? So this is phi n, and this is okay. So what is this? So say that phi n minus 1 is a conformal map that takes the unit disk. So this is the unit, or more precisely the complement of the unit disk, to the complement of the unit disk with some aggregate going on it. So some beautiful aggregate of the type that we've seen before. So then, what is phi n? So for phi n, what do we do? So look at the definition. Phi n is phi 1 composed on phi 2 and so on composed on phi n. So phi n equals of z equals phi n minus 1 of phi n minus 1 inverse of phi n, let's write it like this, of z. And what this means is that we take this picture, this aggregate, we project it back into the unit disk. That's the inverse here. Project it back into the unit disk. Then on the unit disk, we choose a uniform point. So maybe it will be this point. To this point, we add a little interval of length delta n, or just delta if it's alpha equals 0. And then we apply the phi n minus 1 again, which means that the function phi n minus 1 is going to work on this little interval. So the interval would be put maybe here. So what we did, we grew another little particle on the aggregate, where the location where we attach the particle is sampled according to the harmonic measure. So it's like the DLA. And the shape of the particle, of course, is deformed a little bit because of the conformal mapping. It's no longer this beautiful interval that we had before. So that's the so that's this function, and this is in fact exactly what's written here. So it's time 2. So at time 2 we have the aggregate, which is these two lines coming out, and then okay, what you see here is exactly what I did on the other board. Okay, so that's HL0, and HL0 has nice properties that enable us to prove a lot on it. So one nice fact is that HL0 is one-ended. So we can run the process, the aggregate, up to time infinity, and look at the topology of what you got. And there's one path going from the disk all the way to infinity, and a lot of finite trees decorating this path. So that's one thing you can prove. And there's a lot of other things that you can prove. So for example, you can prove that the scaling limit is a ball. That was done by Norris and Turner in 2012.
As I understand it, that's something of a disappointment, right? Because that means that it doesn't represent what you hoped it would represent.
True. Then you can prove a small particle limit, which is the Brownian web. That's again the same paper of Norris and Turner. And it can also prove that the expected size of the nth particle is roughly, it grows exponential in n. So the first, so that's maybe, so the scaling limit as a ball was mentioned that it should be a disappointment. The fact that the expected size of the nth particle grows exponentially in n is an even larger disappointment.
Now, what is a small particle limit?
The small particle limit, so we had here a parameter, delta. So the basic conformal map takes the complement of the unit disk to the complement of the unit disk with a little particle attached to it. And this delta could be taken to be very small. So the small particle limit is when the disk remains the disk, but the particle that you add becomes very small. And it's not the same as the scaling limit, because in the scaling limit you somehow would reduce the disk together with the particle. But here you change the ratio of the disk, of the size of the disk and the size of the particle, and therefore really change it. You really change the behavior. So that's a small particle limit. So the expected size of the nth particle grows exponentially, which means that it's a nice model to work on, and there's actually beautiful mathematics on it, way beyond what I've written here. But it's not a physical model. There's no physical system of aggregation where the particles grow exponentially. Okay, so now I would want to go to our work, to the topic of this talk. So that's a stationary Hastings-Levitov zero, and that's joint work with Yaakov Kagan, Evetar Porkacha, and Amanda Turner. And what we want to do is to construct a version of the Hastings-Levitov process on the half plane, where the seed is the entire real line. So what is the motivation behind this? So first of all, I go back to the picture that I presented in the beginning. So if you look at a natural phenomenon of aggregation, then all the classical aggregation models start with one point. But in reality, those might start from one point and might start from any other shape. And one reasonable shape to study is a straight line, as also was done experimentally in this picture. The second motivation is to look, so just study the same Hastings-Levitov process that we had before, but I want to study the small particle limit at an early time. So I consider the standard Hastings-Levitov zero process, and I take the size of the particle delta to be very small. So in this picture, you see the disk and a little particle, which I hope is visible. For me, I probably need new glasses. For me, it's not really visible, even though I drew it. But then you can rescale this. So if you rescale this, so that the particle would get into size 1, then the ball would get into radius 1 over delta. And except for the rescaling, nothing in the process would change. And then at the delta equals 0 limit, the boundary of the disk would become a straight line. So the small particle limit at early times would be a Hastings-Levitov zero process starting from the real line, whatever this means. So that's the second motivation. And the third motivation is the tractable counterpart of the stationary DLA. So you can define a DLA process starting from the integer real line in the plane. So where particles perform their random walk, and stop when they attach to the line. And it's not a very simple, it's not easy to prove that it's well defined, but it is well defined. And just to mention two important works on that model, I would mention Procaccia-Ye-Zhang, who proved well-definedness and who proved relation to some DLA model with the finite seeds. And another work is by Kozma and Manolescu, who proved that the trees are finite. And I will not get into it. And then the same way that the Hastings-Levitov should be a counterpart of the DLA, the stationary Hastings-Levitov, the one starting from the real line, would be a counterpart to the DLA and would be mathematically tractable because the Hastings-Levitov zero is tractable. And the main issue that makes the Hastings-Levitov in the plane, what makes it non-physical is the growth of the particle size. And what we're going to show in particular is that in this half-plane model, in the stationary model, particle size certainly do not grow exponentially, but in fact do not grow at all. So that's going to be a tractable counterpart of the SDLA, and an important open problem, which I'll present later, is to see that indeed they have somehow similar behavior, which rough simulations suggest they do. Okay, so how do we want to define the stationary Hastings-Levitov? So we want to construct the stationary Hastings-Levitov zero as a composition of conformal maps from the half plane. So the half plane, so now we live on the half plane. We start with just the real line. So the half plane, the open half plane is the complement. And we want to add again and again a slit map. So I'll define what a slit map is. So we take P to be an intensity 1 Poisson point process on 0 infinity times r. What is 0 infinity times r? So you can think about it as the half plane, but it's not the half plane. Well, we don't mean it to be the half plane. So 0 infinity is the axis of time, because at time there are always new arrivals, and r is the real line, is where these arrivals occur. So that's the Poisson point process, and A would be the random set of points sampled by the Poisson process. We will discuss it later, and then we define the slit function as this function, s tilde z equals the square root of z squared minus 1, and what does the slit function do? The slit function is the function that takes the entire half plane into the half plane minus the interval from 0 to 1. So I just add a little interval to the line. So that's this s tilde, and we want to do it not only at 0 but at any point. So s tilde x is the same thing. And so it's a conjugation. It's the same thing, but I add the slit not at 0 but at the point x. Okay, so that's the slit function. And now the pseudo definition of the stationary Hastings-Levitov is the following. So again, let P be an intensity 1 Poisson process. Then we want to define the SHL0 as the following family of conformal mapping from H to, not to itself, but to subsets of it. So we start with the identity. So we start with a function that just takes the half plane to itself. And then if there is a Poisson point at Tx, so if there's an arrival at the point, if there's an arrival at time t at the point x, then we want ftz, okay, here there's a mistake, it's not ft, it's ft minus. We want what happens at time t, the function at time t, at the point z, to be at ft minus. So what happened just before time t, but applied not to z, but to s tilde of z. And what's that going to do? It's going again to take to grow a little slit at the point ft of z, ft minus of z. So, and then the aggregate is h minus ft of h. So what's the intuition behind this definition? Whenever the Poisson clock rings at the point x, we grow a particle at that point, or more precisely, at the image of that point by the function until now. Okay, so that's how I want to define it. And since everything happens in, we work with the Poisson clock, and the set of arrival times is dense, the well-definedness is an issue. So we should worry on how to actually define it. And so we write an explicit definition. So the axiomatic definition of the HL0. So a Cadillac process from T to the Cadillac process ft. So at every time T, I get a function ft. It's called SHL0, or in blue I have the backward SHL, and I ask you to completely ignore to simply ignore the blue and just look at what's written here in black. So initial condition is we start with the identity. We start with nothing, with an empty aggregate. Then we want the process to be adapted. So so I forgot, of course, that there's a Poisson process in the background. So in the background, there is the Poisson process that we said it. So everything that my process does between time s and between time t is measurable with respect to what the Poisson process does between time s and time t. So the Poisson process determines the growth of the process. And then there's a growth condition, and it's it's a technical growth condition that I still want to spend a few minutes, which I do not have on it. So the growth condition is, so let ATN be, A is the set of arrival times of the Poisson process. So all the arrivals which are at values that are an absolute value less than n. So all arrivals between -n and n. So then the arrivals between -n and n up to time t is a finite set. So what I really want to say for the growth condition is that what is ft of z? Ft of z is z plus, ignore the limit. So ft of z is z plus the sum over all of the arrival points Sx of what the what the slit function does at the point z. So that's sort of a standard definition. But of course, that's an infinite collection. And it turns out that if I look at this expression here, what I want to sum, this expression that I want to sum, Fs minus, so Fs minus Fs, well, this expression here is approximately, let's see if I can write on this as I hoped I should be, I would be. So this is approximately 1 over z minus x. So I don't know if this is visible. So the order of magnitude of this is approximately 1 over z minus x, which means that this sum, if I take the infinite sum, is not absolutely convergent, but it might be, but it might still be, be conditionally convergent. And if it's conditionally convergent, then I need to tell you what the order of summation is, and that's why I take the finite sum and then let the limit to go to infinity. And it's important because if instead of the points between -n and n, I would have taken the points between -n and 2n, this would be a different order of summation, and this would have given me a drift of log 2 for the entire process. Okay, so that's the definition. So now I gave you an axiomatic definition. So when you give an axiomatic definition, you need to show that it actually exists. So here's the theorem. It exists and it's unique, in distribution. So we have a process. And what can we say about this process? So here's one of the ways that we have to prove existence, which is just saying, look at the process that's only determined by arrivals between -n and n. So this is well defined because at every finite time you have only finitely many arrivals. And then you want to take n to infinity, and it turns out that it is a Cauchy sequence, so you can, so there's convergence to something. Okay, so what can we say about this process? So that's actually, I hope to have more time for that. So maybe the most important thing in our opinion is that the sizes of the particles don't grow over time. So the distribution of the particle size is tight. And why is this true? So I will not give you the proof, but I'll explain intuitively why it should be the case. So intuitively, if I look at the function ft of z, it turns out that it's just z, so that to the first approximation, it's z plus some constant. So it's z plus a constant, t times, so t times a constant, plus, and then it's the essentially the Maclaurin the Maclaurin expansion. So now it's something times z inverse and so on. So what we see is that this function does not. So if it was only this z plus this constant, then if I look at a small interval, it doesn't become bigger. Now, of course, there's all the other terms that might cause damage, and then you need to prove that they don't cause damage. So they don't. So the function does not blow the particle. If you compare it to the classical Hastings-Levitov, the expansion would be that it's exponential in n times z plus lower order terms. And of course, the exponential, of course, what you get is that the particle, so is at least the first order term blows the particle, but by this amount, which causes the exponential growth, and the lower order term don't save you in that case. So that's the intuition why the size of the particles is tight. And then the same way that you can prove that the classical Hastings-Levitov is one-ended, we can prove that all the trees are finite. So what happens is that we have a growth of trees. Maybe I'll go back so that you see the picture. So that's essentially what it looks like in simulation. So every time, so new leaves are being added to each of the trees. But if you look up to wait up to time infinity, all the trees are finite. What happens is that, for example, you see this tree here, or this tree, it got blocked. At some point, it could never grow because other trees take the sunlight from him.
So the maximal
tree happen to every tree.
The maximal tree is growing to the size of the maximal tree is growing to infinity.
So the size of the maximum tree will go to infinity, yes. But every tree will eventually stop growing. So all trees are finite, but okay, that's I will not explain the notation here. But if you look, so all trees are finite, but if you look at the expected size of a given tree, the expected size of a given tree is infinite. So you have so the trees are finite, but you don't have to go very far away in order to find pretty large trees. That's proof. Then so that's basic geometric properties. Then we can prove a scaling limit, and okay, I'll speak about it. And for the scaling limit, if we just scale the entire half plane linearly, our scaling limit would just be straight lines. Not uninteresting because those straight lines have some finite length. It's not uninteresting, but that's what it looks like. More interesting is if we scale the imaginary axis by n, and the real axis by square root of n. So if we do a Brownian scaling, then the path from Embury Z to the real line would scale to the graph of a Brownian motion. And under the same scaling, the collection of all paths would converge to the Brownian web. So this we essentially know how to prove, but we never wrote down the proof. So that's the scaling limit. And then from the scaling limit, we can go back to the finite to the before scaling state, and we can ask about the behavior of the tree. So what's the height of the tree, of a typical tree, and what's the number of the particles? So the probability, so this is, so the probability that a given tree has height more than h is order of magnitude of h to the minus 1/2. This follows immediately from the Brownian Webb scaling limit. Then another fact is that, which needs to be more properly phrased, typically a tree of height h contains order of magnitude of h to the 3/2 particles. So yeah, well, we all know how to precisely write these kind of statements. And then if you combine these together, you get that the probability that there's a tree, well, again, we should write it, since the trees start at random places and the probability of a tree starting at the given place is 0, you need to be a little careful with how you state things. But probability is a tree emanating from so the probability that a given tree has more than k particles is approximately k to the minus 1/3. So that's about the size of the tree. So I told you that the trees don't have, the size of the trees don't have first moments, but here is a more precise statement of what kind of moments they do have and what kind of moments they do not have. And that's everything that I wanted to say. I'm also slightly out of time. I just want to finish with a few open questions and conjectures. So one question of the mention, that's somehow an old question, because now essentially we know this. So if you properly define the mention equals 1.5, but it's no longer a conjecture. For the stationary DLA, so the process that we hope to, that our process is close to, it was measured the simulation by Mikin and measured to be within this interval, and 1.5 is inside this interval. So our result does match the measurement of Mikin. Okay, I did not speak about Hastings-Levitov alpha too much, but the half-plane Hastings-Levitov we only defined for alpha equals 0, and it was enough of a technical nightmare for alpha equals 0. But then you can ask for the much more complicated case of alpha not equal 0. Is this, how do you define it? Or is it even well defined? So I can still write the axiomatic definition for alpha not equal 0, but then you can ask, does there exist a process satisfying these axioms? And we conjecture that it is well defined for certain values of alpha and not well defined for other values of alpha. And here I wrote our strongest conjecture. We also have some weaker conjectures, but the strongest conjecture is that there's a phase transition at 1, and we do not conjecture what happens exactly at the point 1. Then we can ask, what is the interface of the process? So the process grows over time. So at time t, it typically reaches height of pi over t. But of course, it's a random process, so there's some interface at time t. And the question is, what does this interface look like? And this question was answered for the classical Hastings-Levitov 0 by Victoria Silvestri. She completely identified she completely identified the interface in the limit. And among the authors of this work, there's disagreement whether we conjecture that it is the same or that is not the same as what happens for the classical. I actually do not agree with the conjecture written here. And maybe the most important conjecture, but we have at this moment no approach on how to prove it, is that the long time behavior, and I'm vague, partly on purpose, the long time behavior of the SDLA and that of the SHL0 that we define here are the same. So maybe that in the sense of scaling limits and so on. But since I don't know how to prove it, I don't even phrase it very precisely. And that's everything that I wanted to say. So thank you very much.
The speaker. Any questions?
Yeah, so can I make one, it's not a question, it's a comment from something that Noam said at the beginning. So recently, I mean, recently would be a few years, maybe 2-3 years, some physicists did a simulation. I chanced upon this on the web for the actual DLA model in the plane. And they claim it's the largest simulation ever done. And also it was quite large. I think it was in the billions of particles. And they claim that the limiting shape is just the axis. So it's just a cross. This conjecture of arms should be experimentally falsified for the original DLA model.
So the 5-arm conjecture, I also wanted to comment, the 5-arm conjecture
yes,
for the off-lattice one.
This means that there are 4 arms, but what you say is means in some sense that the DLA, that the lattice DLA is not the right model to look at. Right. Because
well,
it means that it actually sees the lattice.
Yeah, this you already knew. This you already knew with older simulations, even probably from the 90s, where you could see differences in the hexagonal lattice, triangular lattice, and the square lattice in the number of arms. So DLA is very sensitive to lattice perturbations. Probably has to do with the fact that why it's so hard to analyze. But I just wanted to comment that they kind of did I didn't check their algorithm, you know, they needed a lot of shortcuts to get such a large simulation.
Yeah.
So I don't know if they did it mathematically, you know, if it was proper or not. I just saw the picture. When you see the picture, you are convinced that if the algorithm is correct, then the limiting shape is just, you know, 4 arms on the axis. It hugs the axis. So, you know, I don't know what to say. I don't know if this has any consequences on trying to prove things in other models where you conjecturally would try to, you know, maybe it's not a good way to chase something wrong. So, that's the comment I want to make.
So I would believe that a continuous DLA is the off-lattice DLA is a more interesting model. And then I would ask, so I don't know how to prove anything. I don't know how to prove that there are arms and so on, but it seems that there are arms. I would ask even, is the number of arms an almost pure constant in the continuous time, in the continuous, the off-lattice DLA? Because if you have a lattice, somehow the lattice forces the shape and therefore also the number of the arms. But in the off-lattice case,
it might be that for different little particles that you choose, it might be different number of arms.
That's true. That's true. I agree.
So if I can make one comment for Ariel's question. So the conjecture, the physics conjectures for 5 arms is for the off-lattice DLA, and also the estimates of the dimension, which was the 1.7 something. In the paper that you mentioned, which they do the simulation with 10 to the 8 particles, the dimension indeed goes down and it gets very close to our 3/2 estimate. And one can ask whether for the lattice DLA, because Noam, can you unshare for a second? I'll show this picture.
Yeah.
So maybe if you really restrict yourself to the lattice, then what you see here in the middle of the arms looks like the stationary DLA, which, according to what Noam said, right, if it indeed has the same limiting behavior as the stationary Hastings-Levitov, then maybe you will get the 1.5, and then if you make a huge simulation of DLA even larger than this, maybe the dimension will converge to 1.5. But as you can see in their simulation, it doesn't really converge to a cross. So if you put like a bend around it, it looks like this. Right. So here it's fatter than in the beginning and the end. So it looks like this ninja shuriken shape, which makes it much harder.
The fatness is somehow seems to be linear in the diameter.
Mm-hmm.
But it's very hard to tell. The thing is that, okay, we have here a simulation of 1 billion particles, and what we know is that it's very different from simulations of millions of particles. But right. What would happen if you now multiply this by 1,000? Will it still look like this, or will it be, again, a completely different thing? Mm-hmm. So in some sense, it's more of a negative result than a positive result, this kind of...
Yes, so the physicists call this the anisotropic DLA, saying that it's not the physical model indeed. Okay, we'll unshare. Okay.
Yes, Pete.
Thanks a lot for the talk. It was very clear. So the first question is, in the definition that you gave, it was obviously important in the way you took the sum. So you took n, the same distance on both sides. And okay, obviously it's a natural choice, but in some sense it makes me wonder, like, is it canonical? Like, is it an arbitrary choice in some sense?
That's a good question. So one thing that we tried to do is but we did not get a conclusive answer. We did not manage to prove what we wanted to prove. Okay. But I still think the statement is correct. If I say that, if I don't write the entire sum for the growth condition, but I say that at every arrival point, ft equals ft minus composed with the slit function, okay. And I require translation invariance and invariance to reflection.
Okay.
Then I think that this, so clearly the model that if I require the thing with the sum, it implies all of those things.
Yeah.
And I think that I think, but I don't know how to prove that the implication also goes the other way.
I see.
So translation invariant and reflection invariance should imply that. And in this sense, it's not such an arbitrary choice.
Okay. It seems you could also perhaps do things in a periodic way. Obviously, you have problems because you work with the complex plane, but you could imagine that you take n to sort of be your cylinder width, and that each time you map, so you have your configuration on the cylinder, but then at each time you could map it to the half plane by just doing things in a shift invariant way. So it's deterministically shift invariant. And then you could, for example, attach a single particle and see how it works, and then map it back to the cylinder, and then take a limit in n. Do you think something like that would give the same limit?
Yeah.
Okay.
Yeah.
Okay. So, okay. Yeah. Thanks.
It really should give the same limit. So Vital played with it a little bit. I don't remember what exactly the results were, but we're rather confident that it should be the same limit.
Okay. I have one more question.
Mm-hmm.
So in the open questions, you spoke about the interface. So I don't know if this is the same, but you could, for example, imagine that you sort of grow your thing, but you want to have a certain limit, but you don't rescale anything at all. So you look at exactly the same skill, but for example, you sort of change the origin. So you're always at the frontier. So for example, you could take the 0 point and then move up to the last time that you hit your shape, and then sort of your view at that point. Is that the same as the interface that you spoke about? And does that give a sort of limit?
Essentially, so if I understand you correctly, what you suggest is to take the 0 point and ask where the function ft put the 0. That's a random variable, and to understand this random variable.
Yes. Yeah.
And another thing that you can do is to say, okay, my entire aggregate is what the function does to the entire real line.
Okay.
So I can try to, but that's a little too rough. And what people usually do, understanding the interface, is just take not the real line, but a line which is slightly above the real line.
Okay.
Then this line is inside the domain of definition of the function. So when you apply the function to it, things look much better.
Yeah.
And this could be very nicely analyzed, and then you can take the height of the initial line, make it converge to 0, and then and this has been analyzed for the original. So it's essentially a slightly more complicated thing than what you suggested, but it's the same spirit. And for this, you can get a there's very good understanding of that. That's the work of Victoria Silvestri.
Okay.
I do not want to exactly explain what you did because I will not be able to do justice to the work.
Thank you.
Any more questions?
Now, is there a way to get that the particle sizes are tight by some soft arguments, that there is no room for ergodicity, like the arguments that the trees are all finite? Or
that's a good question. I don't know of such an argument, but it would be worth looking for such an argument. I mean, we have a very rather complex argument, and if we could replace it by a soft argument, it would be very nice. But yeah, we should think about it. Doesn't look implausible.
yeah, but not implausible, and I don't know how to.
Yeah.
Any more questions? If not, so let's thank Noam and Pete again. See you all next week, same time.
Thank you.
Thank you very much.